So my name is Mateusz Susik. Today I will describe for you two new gradient boosting libraries, LightGBM and Catboost. You might notice that in the title there is a question, and if you know the Betteridge's law of headlines, usually you might suspect that the answer is no. However, in this case, actually, you might have good reasons to switch to LightGBM or Catboost. Okay, so let's start with a small introduction about me. My name is Mateusz Susik. I'm currently a data scientist at McKinsey Company here in Warsaw. In the past, I used to work in different places. I used to work at CERN. I used to work at Max Planck Institute. I used to be also a software developer. Currently, I'm doing mostly machine learning. And my today's presentation will be split into three parts. Firstly, I will tell you about the XGBoost, the theory standing behind the XGBoost, how it's implemented. It's crucial because those two new libraries that I want to describe, they take inspirations from XGBoost. They are basically more or less the same algorithm with small improvements. So then I will describe the new algorithm, the new libraries, and in the end I will show you benchmarks. I have a lot of them. And why do I want to cover those new libraries? So first of all, although they're quite young, they already managed to be very successful in Kaggle competitions. So for example, LightGBM already won the Spellbank Russian housing market contest. Catboost was in the top of Instacart market basket analysis. And believe me, those are young libraries. Moreover, I use all of those libraries in my work. I know when to use which of them. And I'm not an author of any of those, so my comparison will be fair. At least I hope so. Okay, so let's start with the theory of gradient boosting. So I hope that you are all familiar with decision tree classifiers. And as you know, decision trees work very well with nonlinear data. The problem is that a single decision tree can very easily overfit your dataset. So here you have an example. This example comes from scikit-learn's documentation. And you can see that if we build a deep decision tree, it's very prone to outlying observations. So usually people deal with this problem by building ensembles, so by using multiple trees. One of ensembles is gradient boosting. So here is a very naive sketch of gradient boosting. This is something that you can implement if you have a ready-to-go implementation of decision tree classifier in like half an hour. So what we do, and let me grab the pointer. Oh, great. So we take our data, y is the dependent variable, we feed a weak learner, so like a shallow decision tree, yeah? Then, as shown on this example, here in the bottom, we end up with some kind of a model. This is this squarish line on this image, and we end up with some kind of an error. We call this error residuals, and what we do later, we take another model, so for example here, F2, and we fit it to our residuals, so only to this part, yeah? And we repeat it many times. So H is here the residual, F is the model, and Y is our dependent variable. Okay, but this is not actually how XGBoost works. XGBoost is a bit more complicated, and in order to explain it to you, I will follow a very nice introduction by Mr. Tianqi Chen. It's called Introduction to Boosted Trees. I really recommend it to all of you. So Mr. Tianqi Chen is author of XGBoost, and he firstly observes that, well, if you have an objective for a classifier, you usually can split it into a training loss and a regularization term. So in case, for example, if you have some kind of elastic net model, in training loss you have some kind of square error, and in regularization term you have a sum of L1 and L2 penalties, yeah? So here, in order to simplify a bit, I will use the square loss. And there is one more assumption that we will do. So if we build k regression trees in gradient boosting, each of the tree will have its own regularization term, which will be like used only for this tree. Okay, so training a gradient boosting is an iterative process. Here I will describe the algorithm for decision trees. And the final prediction is basically the sum of the predictions of all the trees. Yeah, you can see it here. So we take the first prediction, and then the second prediction, and so on, and we end up with the final model. So if we take our formula here, we can, this is our prediction, yeah, y hat. This is the prediction of the TIF after the TIF tree. We can basically unroll this formula and put here our, first of all, square loss, and then the prediction of the last but one model and the current model. So using the formula of small multiplication, we can unroll it further. Moreover, some of the things here will be constant. So for example, the y square, this is not something we can really optimize because those are our examples, our observations. So they land here. An important observation here is that you can use any loss that you want as long as it is differentiable. So in our case, it's mean squared error and square loss, yeah? But if you use Taylor approximation, you can take the first and the second derivative. Here I will simply simplify my formulas to use G and H letters. It will make the formula simpler, yeah? And after we remove constants, we end up with something like this, yeah? So here I simply put those terms and change them to G and H. One thing that is left here is the regularization term. We still have no idea what is our regularization term. So let's check what is it. So in order to understand the regularization on decision trees in gradient boosting, we need to provide a notion for the tree. Yeah? So in our case, the tree will be a set of leaves. Each leaf will have its own weight. You can also call it a score. It's a real number. And you have also a function that for each observation tells you in which leaf it ends. Okay? So Q is the function and W are the weights or scores. So the regularization in XGBoost, this term, is basically the sum of L2, L1, and the number of leaves penalties. Now you might notice that those, here you can see some Greek letters, and basically if you ever used XGBoost, those are the parameters that you set. So this is the lambda that you set, this is the alpha that you set, and this is the gamma that you set in XGBoost. On the next slide, I will skip the L1 penalty because the absolute value makes it slightly tough to write down all the other optimizations of this formula. So let's come back to the full formula where we have both the loss, yeah, and the regularization term. Nothing changed. Here we sum over all of the observations. Here we sum over all of the leaves. Yeah, each leaf has its own L2 penalty. I mean the way it is here basically. So then we can change it slightly the order of summing and end up with something like this, okay? And we can simplify it a bit further using other letters. So now we will use uppercase G and uppercase H. And if you have a fixed tree, now it's where the magic begins. So if the tree is set, this is constant, and you end up with a quadratic function. Yeah, where this is the variable, the W. So then you can optimize it. You can say what is the best value for your leaf, for the weight of the leaf. And basically this is what you end up with. And the most important fact, this is something that will be the conclusion of this part, is that in gradient boosting on decision trees, like it's implemented in XGBoost, you do not use entropy or information gain for splits in a decision tree, but you use this gain. So what does it represent? So here is the optimal weight of the current leaf that is not yet split. Here you have the weight of the possible left zone of the split, and here you have optimal weight of the possible right zone, yeah? And sorry, those are like the estimations. And here you have additional penalty if you put this regularization term. So now you can easily say which of the splits are good, which of the splits are not good. Sometimes it might happen that none of the splits are good, that actually you should end up with this leaf and not split further. If you want to implement this, what you do, you sort all of the attributes, and then you linearly basically pass through all the possible values of split and compute the gain. Okay, so end of maths. What are some other tricks that I implemented in XGBoost to make it faster, to make it better? So first of all, when you build a tree in XGBoost, you try to build whole levels of the tree in the same time. It's done because, as I told you, when you compute those gains, you need to pre-sort all of your attributes. If you build the whole level in the same time, you can sort only once. Moreover, you can sort features before one of the levels and then cache the result of sorting and use it while building the next level. Additional thing that is implemented in XGBoost is the shrinkage regularization. So this is actually something that is, I would say, borrowed from gradient descent. Yeah, when you do gradient descent, you want to very slowly go to your minimum. So if you put this shrinkage parameter in your XGBoost, it will kind of follow the idea from the gradient descent. And this prevents overfitting, obviously. There are some things that I did not cover about XGBoost. So first of all, XGBoost offers a GPU implementation that is sometimes faster on large datasets. One of the libraries I will describe soon also offers a GPU implementation, so LightGBM. Other thing is that XGBoost is very well optimized for parallel and distributed computations, but that's probably something you know well. Okay, so let's start talking about the new libraries, yeah? So firstly, I will describe LightGBM. So LightGBM, this is the library that comes from Microsoft. The aim was to make gradient boosting on decision trees faster. And how did they achieve that? So their idea is that instead of checking all of the splits while you basically want to create new leaves, you check only some of them. So before they build a tree, they sort all of the attributes and then bucket the observations. They create bins, yeah? And when they want to split a leaf in the tree, they do not iterate over all of the leaves, but over all of the buckets. So there is a much smaller number of splits considered each time. Another thing is that once you switch to this bucketed implementation, it's actually called histogram implementation by the authors, you can very easily improve your optimization techniques for sparse data. And as you know, if you do some kind of one-hot encoding often, most of the data is sparse, most of the data that we deal with. Then in LightGBM, actually the trees are not grown in this breadth-first fashion where you try to build the whole levels in the same time. They try to optimize it a bit, and they build firstly the leaf that provides the biggest difference in the loss. One more important thing here is that XGBoost already has the histogram method implemented. It's not by default, so if you want to use it, you need to switch the tree method parameter to hist. Okay, the other library that I would love to present to you is CatBoost. It's developed by Yandex. It's a very fresh library. The first release was September 14th. They had a different idea. Instead of making it faster, they wanted to prevent overfitting. As you know, gradient boosting can from time to time overfit, despite the regularization techniques that you have there. And how did they achieve there? So first of all, they have more sophisticated handling of categorical variables, but also they noticed that in the gradient boosting you have a thing that is called the gradient bias. So they ran a very small experiment that is shown on this chart. They basically created this distribution that they can sample from. They took a single sample and trained their model, the XGBoost-like model on it. And this is represented by the solid blue line, and you have the mean squared error on the y-axis. Then they decided to do a similar training procedure, but on each iteration, so for each tree in the experiment, they sampled a new data set from the distribution. So it's like if they had infinite data set. So it's obvious that such XGBoost-like algorithm will perform better because simply the training set is larger and it does not catch any noise from the data. So the authors of CatBoost found out how to improve over XGBoost if you have just a single data set, and they built an algorithm that maybe not fully fights this gradient bias, so it does not fully fight the problem with the correlation between your model and the noise, but it at least approximates the perfect solution. How do they do that? So first of all, they use a data structure that is called oblivious trees. Oblivious tree is a decision tree where on each level, all of the splits are the same. So in a normal decision tree, if you have a single level in a tree, all of the splits can be different. In oblivious tree, it's not true. And the second thing is that for each tree, before they train it, they randomly permute all of the observations, and therefore each of the observations, if they compute the gradient, they compute it only on the preceding samples. Okay, so those are the main things that are improved in CatBoost. So let me now switch to benchmarks. So we want to compare all of the three libraries. Firstly, I will show you some of the benchmarks done by different people, not by me. This is the benchmark done by one of the bloggers, and she compared LightGBM and XGBoost. She compared them in terms of the time of execution. So what you can see here, this small blue field here is the time spent by LightGBM. And this brown field is the time spent on the XGBoost, on the Bosch dataset, one of the Kaggle competitions. And on the x-axis, you have number of threads. You can easily tell that that LightGBM is much faster. One important thing here to note is that XGBoost implementation here did not use the histogram method. So it compares with the original XGBoost. So as you can see, the speedup is sometimes 12, 13 times. So this is training time. Well, usually prediction is much faster than training, yeah? And here you have a perspective of authors of XGBoost library. After they implemented the histogram method, they compared it to the histogram method of LightGBM. And here is the AUC. Here are the AUC scores of both methods. As you can see, they have very similar scores. The only interesting difference is in case of the Higgs boson dataset, where the method that is guided by the loss, so by the maximum difference in the loss in LightGBM, they perform better than the original XGBoost algorithm. They also compared the execution times of histogram method in XGBoost and LightGBM. And first of all, they usually take the similar amount of time, but there are still datasets, usually datasets with large number of parameters, where LightGBM is much faster. And this is the example of Yahoo Learning to Rank dataset. And then there is a benchmark done by Catboost developers. They compare log loss on different datasets, and they claim that their algorithm is better than all of the others on all of the datasets. Very important thing here to notice is that if you have default parameters in Catboost, so for all of these parameters, when they say that something is tuned, it's tuned with Bayesian optimization. And they use like 5,000 iterations, 5,000 trees in their experiments. The important thing is that default parameters of Catboost usually outperform tuned versions of LightGBM and XGBoost. So the point is that usually I do not trust benchmarks. I only trust my own benchmarks, so I decided to prepare one. I took the Amazon dataset from the Catboost experiment. The problem with this dataset is that it contains only categorical variables, or even worse, it contains only IDs. The features are basically IDs, so you do have to do some kind of one-hot encoding in order to work on top of this. However, in the experiment, nothing like this was done. And I also did Bayesian optimization with a smaller number of iterations on my machine. And I compared three things. I compared the AUC, the training time, and the prediction time. So as you can see, in terms of AUC, Catboost is the best, but only if you manually specify to it which of the features are categorical. Otherwise, it does not perform this well. LightGBM has a similar feature. You can manually tell it which of the features are categorical. I tried it. Unfortunately, the AUC score was worse. And then for the training time, this is unfortunately the biggest disadvantage of Catboost. It's much, much slower. You can see here that, for example, Catboost with categorical variables took 3 minutes. LightGBM takes 2 seconds, which means that basically you can do quite well optimization of hyperparameters with LightGBM before your first iteration of Catboost ends the training phase, yeah? And LightGBM is faster than XGBoost. Here I did not use the histogram implementation of XGBoost. And then the prediction time. So this is very interesting. LightGBM here is slower than XGBoost. The fastest is Catboost, but only if you do not use the categorical features. And there is a very good reason behind this, because as I told you, in Catboost, they use oblivious trees. And they can do much more optimization there. If you are interested further in this, I can explain after the lecture. And one more thing here important is that all of those libraries have very nice scikit-learn wrappers. So they are very easy to use. Okay, so it's time for the summary. So I would suggest a few things for you, for all of you that use gradient boosting in your work. First of all, try Catboost from time to time as it can improve your scores. But maybe even more important, switch to LightGBM or the histogram implementation in XGBoost if you do a lot of runs of your gradient boosting. So for example, if you do feature selection, if you do hyper-optimization of the parameters, yeah, then you can save a lot of time. And one thing that I learned while I was preparing the materials for this presentation is that it's very useful to use Bayesian optimization, whatever packet you prefer. And, well, as probably most of you are not aware, we currently have a data science team here in Warsaw. We are growing. We are looking for new data scientists. We have a very wide variety of projects. Please join us at our booth that is next to other sponsors, and we can talk a bit more about what we do, about who are we looking for, and excite you a bit. Okay, and here is the list of the references. My presentation is available on GitHub. There is a link on the bottom. And I really recommend to you reading, first of all, the Introduction to Boosted Trees by Tianqi Chen. And if you want some more details on Catboost, there is a publication that is called, I hope I put it here. Yes, Fighting Biases with Dynamic Boosting. Those are the two that I would recommend most. Okay, thank you very much. So, any questions?
With the randomized search, how much faster was it actually for you for those libraries?
So to be honest, I did not use random search here, so I cannot tell you the absolute values, if it was like 2 or 3 times faster. But from my experience, it can faster converge. And it basically will find you the minimum, yeah? Because the random search will simply be somewhere close to the minimum.
I'm just asking because in neural nets, it's quite inconsistent if there is any improvement. Like there's a promise that there is, but it's not 100% sure if that promise was ever met. So the same question comes here. Like, is it actually way better? In your experience, I understand that it is way better to use hyper-optimized.
So I wouldn't say it's way better. I would say it's a slight improvement. And obviously, gradient boosting is a different world than neural networks because the models are much simpler. You basically have decision trees instead of a large number of neurons. At least give it a try.
So all the results you have shown were the subject of this Bayesian optimization, right?
Let me browse through them. So my benchmark was on top of Bayesian optimization. This one was as well. Here it does not really matter. I mean, maybe the parameters have a very slight connection with the time spent, but usually if you set the same depth and the same number of iterations, they will have very comparable time performances. And here it was, I'm not sure, but probably also Bayesian optimization. I would have to check this one, actually. Okay, no more questions? Thank you very much.